That is the equilibrium constant for this reaction. Notice anything missing? Why didn't I write water in the equilibrium expression? I didn't write it because it's a liquid. And we don't count liquids. We only count aqueous and gaseous reactants and products, okay? So don't forget that rule when you're making your equilibrium constant, okay? So because weak acids and weak bases, since acid-base chemistry is sort of its own thing, the equilibrium constants for acids and bases get sort of a special notation. So we call them Ka and Kb. Ka for acid, Kb for base. It's just an equilibrium constant, but because it's for an acid or a base, we call it an acid dissociation constant, Ka. But it's the same thing, same formula. And it helps us to actually determine the strength of a weak acid or a weak base. Because the same way that K, the K value helps us determine whether products are favored or reactants are favored. So the Ka, the rule is that the higher the Ka value, the stronger the acid is. But it's still weak. They're still weak acids. But for example, hydrofluoric acid is a weak acid that is stronger than hydrocyanic acid. Okay, they're all weak acids, but these are stronger. And notice that since these are negative exponents, as the negative exponent gets smaller, the number actually gets bigger, because this is 0.01, whereas this is 0.00000175, I think. Sorry, you can't see my font here, my writing, because I chose the wrong color. But just to illustrate that this number is, in fact, higher than these numbers down here. Sometimes negative exponents kind of confuse you momentarily because you think 10 to the 12th, that's higher than 10 to the 2. But 10 to the negative 12 is much smaller than 10 to the negative 2. Okay. So the larger the Ka, again, the stronger the acid is. So when it comes to acid-base problems, remember I mentioned earlier that when you do acids and bases, particularly in an aqueous solution, water can act as an acid or a base. There's always an acid and a base in the problem, okay? And with weak acids and weak bases, since it's a reversible reaction, the products also can act as an acid or a base. So we call them the conjugate acid and the conjugate base. Okay? So, I guess just to show you how to identify acids and bases, we've talked about identifying acids and bases. An acid is a proton donor, and a base is a proton acceptor. Okay? So in this reaction, CH3COOH, acetic acid, becomes CH3COO. So it lost this hydrogen here. It donated it to the water, which became a hydronium ion. So since it's the proton donor, it is the acid. And since water is the proton acceptor, it is the base. Check. We know that. We understand that. We've talked about acids and bases and the Bronsted-Lowry definition, proton donor versus proton acceptor. Now, what happens is this acid, the product of this acid, becomes a conjugate base. Because in the reverse reaction, if we're doing the reaction in reverse, this acetate molecule gains a proton. It accepts a proton. So in the reverse reaction, it is a base. Okay? Same thing with the hydronium ion. In the reverse reaction, it acts as an acid. So therefore, it is the conjugate acid. So acids and bases we identify on the reactant side. And then each of them has a conjugate base and a conjugate acid. And it's always that the acid on the other side of the reaction becomes the conjugate base. And the base, oops, kind of fast forwarded there, the base then becomes the conjugate acid, okay? And so we have these conjugate acid-base pairs that we can draw. The acid and the conjugate base are a conjugate acid-base pair, and the base plus the conjugate acid are an acid-base pair, a conjugate acid-base pair. So, on this one, let's practice. Let's label the acid, the base, the conjugate acid, and the conjugate base. So, HF plus water becomes fluorine ion and hydronium ion. So that fluorine ion must have come from this HF, hydrofluoric acid. So that means that this hydrogen must have been donated to the water, which then accepted it and became hydronium ion. So this is our proton donor. That means it's our acid. And this is our proton acceptor, which means this is our base. Okay? So the hydrofluoric acid donated a proton to become the fluorine ion. So now it is the conjugate base. The acid becomes the conjugate base because in the reverse reaction it is now going to accept a proton. That's why it's the conjugate base. It's now going to be a proton acceptor in the reverse reaction. Whereas the hydronium ion is the conjugate acid. Okay? And I've color-coded it for you so you can see the pairs, conjugate, the two conjugate acid-base pairs. Okay? So here's a little practice, a different way to practice this information, conjugate acid-base pairs. Okay? So for the first one, it's asking you to provide the conjugate acid or the conjugate base of these different compounds. So what is the conjugate acid of OH, of hydroxide ion? Well, the conjugate acid is going to be the proton donor. So if this is the base, it's saying that this is the base. What is the conjugate acid? This is the proton acceptor. So what is the proton donor version? The conjugate base, the conjugate acid is going to be H2O. That's going to be the proton donor version. How about this one? Conjugate acid of HPO4, 2 minus. So that's the phosphate ion, I think. The conjugate acid. So this is the base. Okay, this one is the proton acceptor. Then what is the proton donor version? It's the one with an extra proton. So it will be H2PO4 minus. Okay? See, I've added a proton. The conjugate base of H2S. So if this is the acid, what is the conjugate base? What does it become after it donates a proton? And that would be HS minus, suppose, because it loses a proton, so now it's a base. Now it can be a proton acceptor, the conjugate base. The conjugate base of HCO3 minus, if this is the acid, it's saying that this is the acid. So what is the conjugate base of this acid? Is after it has donated a proton, it becomes this. So hopefully that makes sense. And for this last one, I'm going to go ahead and write out a reaction in case that is helpful for you in solving these, in case you're confused. So what it's saying is, it wants to know the conjugate base of this molecule, so that implies that this is an acid. That this is the acid, and that if we react it with water, it's going to form products being, since this is, it's already telling us that this is an acid, because it's implying that by saying it has a conjugate base, that means that water in this reaction is acting as a base, so it's going to become H3O+. It's going to accept a proton, and from this guy. Alright, so then that means that our conjugate base here. I should say there's 2 minus there. Okay, so does that make sense? So now is it clear? I did them all in my head, but hopefully maybe writing it out makes you visualize it better. So if it's asking the conjugate base of this molecule, it's telling you that that molecule is an acid. And so what I was doing in my head was just kind of drawing out this reaction in my head, but maybe for all of these it might be helpful for you to write out the whole reaction in order to determine the conjugate acid and conjugate bases. So here's another one where we're going to complete the reaction, okay? Complete the following reaction of H2PO4. If H2PO4 acts as a base, label the acid, the conjugate acid, and the conjugate base, okay? So it's telling us that this acts as a base and that we're reacting it in water. We can always assume that we're talking about an aqueous solution and we're reacting in water. So our products are going to be, if this is the base, then it's accepting a proton. So this has to be the acid. I want to color code here. So this has to be the acid, meaning that it's donating a proton. All right, so now let's write our products. Our products are going to be H3PO4. It's getting another hydrogen, and therefore the negative charge is going to balance out. So since it gained a proton that had a plus charge, we canceled out that minus charge. And what's left of the water is going to be a hydroxide ion, okay? So our base becomes this, the conjugate acid, and our acid becomes this, our conjugate base, okay? I hope everyone is still following along with our acid-base chemistry lecture, because we're about halfway there, well, a little more than halfway there. So when it comes to water, I sort of mentioned earlier that water is a very special molecule when it comes to acid-base chemistry, because it can act as an acid and it can act as a base. And that's because of what happens to water, what water can do to itself. Water can actually do what's called autoionization. It can actually become, water molecules can actually ionize each other. So you have these two polar water molecules. The hydrogens have a slightly positive charge. The oxygen has a slightly negative charge. And they're attracted to each other through hydrogen bonding, okay? And that hydrogen bond is a strong bond. It's the strongest intermolecular force, right? And occasionally, very, very rarely, like 1 in a million or something, 1 in a billion water molecules, the water molecules, that hydrogen bond will actually, like, physically become a covalent bond. How do I say it? One water molecule will actually steal, the hydrogen bond will be pulling so hard on that hydrogen that one of the molecules will actually steal the hydrogen off another molecule. So that's what happens. And what results is a hydroxide ion and a hydronium ion. So a base and an acid, essentially. Which is why water can act as either a base or an acid. So this happens in water, in pure water. This happens, very infrequently, 1 in like a million molecules. But still, if you have, in this bottle of water, I have way more than 1 million molecules. So there's definitely some ions floating around. So the equation, the chemical equation, this is the sort of diagram equation, but the chemical equation for autoionization of water is 1 water molecule plus another water molecule can become hydronium, 1 hydronium plus 1 hydroxide ion. So the equilibrium constant for this reaction is fairly small. It's 10 to the negative 7th, 10 to the negative 14th, 10 to the negative 14th, which is pretty small. Okay, so that's not 1 in a million, that's like 1 in I don't know, 1 in 10, whatever 1 with 14 zeros is, like 100 million trillion. I don't know my numbers that high, okay? 1 in 100 million trillion molecules will actually dissociate. So that's what this K value means. So remember we said the equilibrium constant for weak acids is called a Ka. So the equilibrium constant for the autoionization of water is called Kw. And it is written like this. This would be the equilibrium constant expression. Since water here is a liquid, but these ions are aqueous, only the products show up in the equilibrium expression, okay? And the Kw for water at room temperature at 25 degrees is 1 times 10 to the negative 14th. It's a very small number. So water is a very, very weak acid or base, I guess. It has very, very weak power. And because it has such a small concentration of ions, pure water, like truly pure water, is actually a very poor conductor of electricity, which I think is sort of counterintuitive because we all know, like, you're not supposed to drop the toaster oven in the bathtub, okay? That's because tap water actually has a lot of ions, a lot of minerals, like fluoride and chlorine. All of those things are added to our tap water to help purify it. So tap water actually has a lot more higher ion concentration than pure water does. So that is just the Kw, the ionization constant of water. So when it comes to talking about acidity and basicity of a solution, of an aqueous solution, we're really talking about how many hydrogen ions, or how many protons, or how many hydronium ions. Those are all synonyms, okay? Proton, hydrogen ion, hydronium ion. Okay, they all mean the same thing. So what we're measuring, really with a pH meter, with a pH indicator, is how much hydronium ion is in a solution. So if you have equal amounts of hydronium and hydroxide, as you do in pure water, then the pH is, or the concentration of each is going to be 10 to the negative 7th, okay? In pure water, that is the concentration of both hydrogen ions and hydroxide ions. They're equal, so you have a neutral pH, a neutral solution. In an acidic solution, you have more hydronium ions than you do hydroxide ions, and that defines an acidic solution. And a basic solution is the opposite, more hydroxide ions than hydronium ions, okay? So pH is measured on a pH scale, and it is related to, again, it's related to the concentration of the hydronium ions or the hydrogen ions, either way. So I guess what the pH is, so when we're talking about concentration of hydronium ions in a solution, it's always a small number. It's 10 to the negative 5, 10 to the negative 12. These are very small numbers, and they're kind of awkward numbers to work with mathematically. It's much easier to see things in a different format. Hi, sorry, giving a lecture on video. Can I have another, like, 40 minutes or so?
Are you doing a class?
Yeah. I'm filming for my class, so I'm pre-filming.
Okay, thanks.
Can you come back in like 40 minutes? Sorry, guys. Interruption there. So, as I was saying, the pH scale, we convert it using log function so that we have easier numbers to work with. Negative 1 through 14 are easier numbers to work with than 10 to the negative 1, 10 to the negative 14th, okay? So that's why when we talk about pH, the pH scale is like 0 to 14. We rarely ever talk about negative pHs. So the calculation to calculate the pH is just taking the negative log of the concentration of the hydronium ions. And notice there's a pattern here. The negative log of 10 to the negative 4th is a pH of 4. The negative log 10 to the negative 5 is a pH of 5. So the negative log of the hydronium ions is going to be around what the exponent is for the concentration. That makes sense. We'll do some problems. But essentially, the pH scale is just an easier way to look at things than the concentration of the hydronium ions. We've just done a little conversion. So let's look at these and determine whether or not these solutions would be considered acidic, basic, or neutral based on either their pH or their hydronium ion concentration, okay? So a pH of 5, and I guess I should go over this before we do the problem. Neutral is a pH of 7. Anything below that is acidic. Anything above that is basic. So any pH below 7, 1 through 6, is acidic, and 8 through 14 is basic. So a pH of 5, would that be acidic or basic? It's below 7, so it would be acidic. How about B? If the hydronium ion concentration is 2.3 times 10 to the negative 9th, would that be acidic or basic? Well, we could go back and look at the scale. We could also calculate the pH. You can do a mental calculation here and say that the pH is going to be about 9 because the exponent here is 10 to the negative 9. So the pH is going to be about 9, which means it's going to be basic. It's actually going to be, I think, a little bit less than that. I always get confused whether it's a little bit less or a little bit more. The pH of 12 is acidic or basic? Oops, sorry, this I meant to write basic. Is basic. pH of 12 is basic. Okay. Hydronium ion concentration of 4.3 times 10 to the negative 4. The pH is going to be about 4. All right. So that would be acidic. It's less than 7. Hydronium ion concentration of 1 times 10 to the negative 7th. That's going to be a pH of exactly 7. So that's going to be neutral. Okay? Neutral. Awesome. All right. So measuring pH. How do you measure pH? We measure pH using a pH meter, or we can use pH indicators, pH strips. Both are valid uses, valid measurements. The pH meter is going to be much more, what's the word? Correct. It's going to be more precise than using the indicators, the papers. But both ways are ways of measuring the hydronium ion concentration. Okay. So now we're going to do a little bit more math with this equation. So how to calculate pH mathematically. So we just did a problem where we sort of estimated it using the pH scale, but now we're going to actually be able to calculate pHs using hydronium ion concentration, and vice versa, doing the flip. If we know the hydronium ion concentration, but we want to find out the pH, this is the equation that we use. If we are given the pH, but we want to know then we want to know what's the hydronium ion concentration, this is the equation we use. It's derived from that one. I'm not going to walk you through the derivation. It's just good to have them both handy. Okay? So everyone should get out your scientific calculators now. This is a part where it's usually a little tricky for people. I usually do a lot of walking around the classroom, helping people use their calculators. Everyone probably has different calculators. I'm going to grab mine right now. I hope. Do I have it with me? I do. I have my scientific, my graphing calculator from high school, actually. So on my calculator, so let's write out the equation first. So we want to determine the pH for these solutions. And pH equals the negative log of the concentration of hydronium ions. Okay? So for A here, we need to type, our equation is the negative log of 1 times 10 to the negative 5. Alright? And some of you may have already done this in your head and figured out that 1 times negative 5, the negative log of that, from our little mental math practice before, is going to be a pH of 5. Alright, but let's practice it on our calculator, especially knowing what the answer is. Let's make sure we can all get that answer, okay? On my calculator, I type in negative log, and then I just type in 1, and then times 10 to the negative 5, you type in the function EE. So I type in 1 EE negative 5, because EE means times 10 to the, okay? So I typed in negative log 1 EE negative 5, and I got the answer 5, okay? Some of you might have to type in the number first, so 1 EE negative 5, and then hit negative log on your calculator, depending on your calculator. So play with the buttons, play with the order of entering things in until you get the right answer, okay? And if you have trouble, email me with what calculator type you have. If I'm still on campus, hopefully you can stop by, come by my office hours, or go to the LAC. Actually, that's a really good option. Ask your classmates or go to the LAC and see if someone can help you there, help you to get the right answer for these, and figure out the order that you need to type it into your calculator, because that's actually the trickiest part of this math. It's otherwise very simple. It's just plug it in to the equation and then plug that into your calculator. Again, on a test, if you write down this equation and you plug in the number and you get the wrong answer on your calculator, I'll still give you partial credit. So don't get too worked up, don't get too stressed out. You can still do this, okay? It also helps that you have an idea of what the answer is supposed to be. The concentration is 10 to the negative 5, so no matter what this number is here, the pH should be around 5, a little below or a little above, depending on what this number is, okay? We'll try that on this next problem. So let's go ahead and just guesstimate, first of all, what the pH should be on this problem. If the concentration of hydronium ions is 5 times 10 to the negative 8, then the pH is going to be about 8. I can't remember if it's going to be a little above or a little below. So now let's plug in, take our equation. pH is the negative log of the hydronium ion concentration. So therefore it's the negative log of, in this case, 5 times 10 to the negative 8. Alright, all in parentheses. And your calculator might need you to use the parentheses as well. So those are all things to try. So I'm typing in negative log, I'm going to do parentheses this time, 5 EE negative 8 equals 7.3, a pH of 7.3, okay? So that's about right. We're not way off our number 8 here, okay? It happens to be closer to 7, but if you got an answer like, 3, you know that you would be very far off. So you want it to be 8 plus or minus 1. So 7.3 is our answer here, pH of 7.3. So again, play with different order of typing this into your calculator until you figure out the right way to do it, or have someone help you in the LAC. But otherwise, this math is really pretty simple. Okay, now we're going to try the other equation. In these problems, we have the pH, we're given the pH, and we need to figure out the hydronium ion concentration. Okay, so so let's write down that equation. If we want to know the hydronium ion concentration, it's 10 to the negative pH value. All right, so in this case, 10 to the negative 7.35. So we plug that into our calculator. So on my calculator, so there's two ways to do this on my calculator. I can either type in 10 and then do the little caret symbol. So I can either type in 10 and then that little caret symbol, negative 7.35. Negative 7.35, and make sure that when you type in the negative that you're not hitting the minus key. There should be a separate key that converts things to the negative. Okay, and I get an answer of 4.466,835. Keeps going. Okay, but I'm gonna just 4.46. Another button on my calculator that I have, that some of you may have, I have a button that's 10 to the x. It says 10 to the x. So I have to hit, for me to get that one, I have to hit second log is 10 to the x. So then all I have to do is 10 to the x and then type in negative 7.35. And I get the same answer. Oh, I forgot to say 4.46 times 10 to the negative 8 times 10 to the negative 8. On my calculator it says E negative 8, which means times 10 to the negative 8. Okay? So just hopefully many of you are familiar with your calculators and familiar with this type of scientific notation in a calculator. But for those of you who don't, I'm trying to add that extra explanation in. And if you're still confused, please go to the LAC and get some help or contact me or a classmate to help you out, okay? So then for this problem, it would be the hydronium ion concentration would be 10 to the negative 11. Type that into my calculator here, to the negative 11. And I get a hydronium ion concentration of 1 times 10 to the negative 11. Okay, 1 times 10 to the negative 11. So that is calculating pH from hydronium ion concentration and calculating hydronium ion concentration from pH. Okay? So I said that pH is just a way of converting the hydronium ion concentration to a number that's easier to work with. We can also do that with acids and bases with their Ka value. We can also convert the Ka or the Kb to a pKa or a pKb by taking the negative log of it. So that P essentially means the negative log of. pH is the negative log of the hydrogen ion concentration, H+. So pH is the negative log of. So the pKa is the negative log of the Ka. And we're not going to do those problems, but just to show you, it can be an easier way to look at acid and base strength. So having a smaller pKa is having a stronger strength in terms of acids. A smaller pKb is a stronger base. Okay? And so sometimes you might see that. So here's some problems. Determine the stronger acid in the following pairs of weak acids. Ammonium ion has a pKa of 9.2. Nitrous acid has a pKa of 3.35. Which one is stronger? The lower the pKa value, the stronger the acid. So this is going to be the stronger of the two. Part B, phosphoric acid with a pKa of 2.12 or dihydrogen phosphate ion with a pKa of 7.18. The stronger one is the lower pKa. Okay? So that's pretty simple there. A lot of times acid strength is mentioned in pKa. You usually get the pKa value as opposed to the Ka value. So there is a relationship between pKa and pH of an acid. I'm debating whether I want to skip this part of the chapter because it's a little bit more confusing. And you know what? I think I am. I'm going to opt to skip it. It's a little more confusing, and I think I'd rather be there in person to explain it and go over it and make sure that you're following. And it's not, I don't think, a majorly important concept. So take a mental note of that. We're skipping over that. Okay, so the last part of the chapter is talking about weak acids and weak bases in nature. Okay, so we're actually getting an introduction into, sorry, I had to briefly remind myself, we're getting an introduction to amino acids and proteins, which are actually going to be the next chapter that we're going to be talking about chapters 9 and 10 next, which is proteins and enzymes. And the building blocks of proteins are amino acids. Amino acid, they have an acid group, an acid functionality. They're acids. They're biological weak acids. They actually also have a base group. The amino group is a base. So they're very versatile compounds in our bodies. So this is the basic structure of an amino acid. It has an amine basic group, and it has a carboxylic acid group. This structure, though, is very rare in nature. More commonly in physiological settings, like in our body, in our cells, amino acids are in this form. The base group is protonated, it has accepted a proton, and the acid group has donated a proton. And since it has a positive charge on one end and a negative charge on the other end, overall this amino acid has a neutral charge. So when you have an ion like this where it has a positive and a negative charge, so overall it's a neutral charge, you call that a Zwitter ion. I love that word. I just think it's fun to say, a Zwitter ion. So amino acids exist mostly as Zwitter ions at physiological pH, which is about neutral. It's like 7.4, okay? So amino acids existing as Zwitter ions has to do with this relationship between pKa and pH, which I've skirted over, but I'm going to still sort of explain in this context. So each of these amino acid molecules have a unique pH where the Zwitter ion is the predominant form. And for most amino acids, that pH, where the Zwitter ion is predominant, is about a pH of 6, okay, which is close to the pH of 7. And then as the pH gets lower, so as you add acid, okay, if the pH is lower, it means the hydronium ion concentration is higher, okay? In an acidic environment, there's more hydronium ions, there's more free protons. So then in that environment, the acid gets reprotonated. There's so many protons around that both the acid and base group have a proton, get protonated, okay? So at low pHs, you have both of the groups are protonated. At high pH, so you are adding more base, it's more basic, there's less free protons around. Both of these groups are going to lose their protons, okay, and have just be deprotonated. And you can see that here on this in this diagram. Again, I'm very visual. I like to see things visually. So anyway, the point at which the pH where the Zwitter ion is the predominant form is called the isoelectric point, or the PI, okay? And the isoelectric point of most amino acids is 6. So if you look here on this slide, what it's showing you is, in blue here, it's showing you glycine is the amino acid that's shown here. So as the pH gets lower, what's going to happen? So let's see. Did I have it in the slide already? No. Okay. So I got to recalculate this. GlyH2 would be this one, where both groups are protonated. So this is GlyH2. And gly without any H's would be this guy here. And GlyH, we're talking about, I'll make it blue, this guy here. Alright, is the blue line. Okay, on the chart. So what it's saying is at the isoelectric point, it's really, the isoelectric point is sort of a range. There's a range here where the predominant form, a range of pHs, where the predominant form is the Zwitterionic form. So that range is what? Like 5 to 8. A pH of 5 to 8. If you're in that range, then the amino acid is going to be in this Zwitterionic form. Now, if you start adding more acid, then what happens is you get more protonation. So you protonate this group, the acid group over here that was deprotonated as a Zwitter ion. And if you add more, if you get more basic, so there's less hydronium ions around, then you're going to fully deprotonate. So both groups are going to be in their deprotonated form. Okay? That's all that this is saying. So I'm not going to really explain about the pKa's of each of these groups, but essentially what it's saying is that amino acids are Zwitterionic in physiological pH because our physiological pH is 7.4, and at pH 7.4, this is the predominant form. This is the happy form for that amino acid, having the basic, the amino group protonated, and having the acid group deprotonated. Okay, so the last thing about about acids and bases is this thing called buffers. A buffer is a chemical, I guess, that it's a solution that contains both a weak acid or a weak base and its conjugate acid or its conjugate base. A buffer is something that resists change in pH because it contains these conjugate acid-base pairs. And buffers are really important, particularly in physiology, because if you have if you have a solution and you add a little bit of acid to it and there's no buffer in it, you add a little bit of acid, that's going to totally cause a big shift in the pH. If you have a buffered solution and you add a little bit of acid, the buffer is going to sort of suck up that acid that you added so that the pH of the solution doesn't change very much, okay? And that's extremely important in physiological systems because we really require our physiological pH to be in a very narrow range, between 7.34 and 7.45 is the range that we can tolerate our body's, our blood pH. So we need to have a buffer system to help steady the pH so that if acid or base is introduced, that we can manage that. So blood is mainly buffered by the bicarbonate system. There's also the phosphate system. There's some other buffer systems in the blood, but blood mainly relies on the bicarbonate system. Okay, so this is how the bicarbonate system works. So in our bodies, metabolism, a product of metabolism is water and carbon dioxide, okay? That's the product of metabolism in our cells, and we'll talk about metabolism in the last chapter. So then we need to expel that carbon dioxide through the lungs, right? So we have to take it out of our tissues, the carbon dioxide needs to get into the blood and then travel to the lungs to be expelled. So when carbon dioxide goes into the blood, we get this equilibrium occurring between water and carbon dioxide, and we mix them. You get carbonic acid and water, which is an acid, so it's slightly acidic. But this is an equilibrium, so it can be, when blood carries this carbonic acid back to the lungs, it then equilibrates back to carbon dioxide and is exhaled as carbon dioxide, okay? So the other component in our blood is we have carbonic acid, but we also have bicarbonate ion to help balance out the pH of the blood, okay? So, and that is the buffer system, the weak acid, carbonic acid, and its conjugate base, bicarbonate ion. That would be a buffer system. It's a weak acid and its conjugate base pair. So what happens to the blood pH when there's improper ventilation of CO2, when I was talking about hyperventilation and whatnot? So if you are, well, first we'll talk about hypoventilation. So hypoventilation is a failure to exhale enough carbon dioxide. So this is in cases of like lung damage, lung disease, like emphysema, smokers, okay? They can't exhale the proper amount. They're not expelling carbon dioxide well enough. So it all comes back to Le Chatelier's principle with equilibria, okay? If you have, nope, I don't have it there, okay. So in the case of hypoventilation, you're not expelling enough carbon dioxide, okay? Therefore, you get a buildup of carbon dioxide. So it's like you're increasing carbon dioxide, and it's going to shift that equilibria then to the other direction. It's going to shift it to the right. It's going to cause a buildup of carbonic acid. So it causes a buildup of acid, and therefore it causes respiratory acidosis. So it's important to have extra bicarbonate ion to help sort of buffer the blood, the pH. But if you don't have enough bicarbonate, then that carbonic acid gets too high, and you actually get respiratory acidosis. Your blood acid levels increase, and it can be very dangerous. Well, I guess what I should say is it builds up this carbonic acid, which then causes a shift this way too, causes a buildup of hydronium ion. That's where the buildup of the acid and the pH can start to shift. The opposite situation is hyperventilation, so where you are expelling too much carbon dioxide and you're not actually inhaling enough. So you're doing a lot of exhaling but not enough inhaling. All right, in that situation, you're not getting enough carbon dioxide. All right, so then the reaction shifts this way. You then have less acid, which causes it to become very basic. Your blood can become basic, which is called respiratory, or alkaline is another word for basic. So that's respiratory alkalosis, having the blood become basic. The common sort of simple home remedy for hyperventilation, when you're hyperventilating, is to breathe into a bag, because then any carbon dioxide that you're breathing out, then you sort of are breathing in extra carbon dioxide. So it's increasing your intake of carbon dioxide. You're sort of, normally you shouldn't do this. Normally you don't want to breathe into a bag, because then you won't get enough oxygen. You'll be getting too much carbon dioxide. But when you're hyperventilating and you're breathing out too much carbon dioxide and changing your blood pH, it's a good thing to breathe in a little extra carbon dioxide. So that's why when you're hyperventilating, they tell you to breathe into a paper bag to breathe. So then you're breathing back in some of that carbon dioxide that you're breathing out to help get this equilibrium back on track. So here's just a table from your book talking about some of the different symptoms of respiratory alkalosis, and respiratory acidosis. There's also metabolic alkalosis and metabolic acidosis, acidification of the blood due to a metabolic disease, some kind of metabolic problem, as opposed to a respiratory situation. Okay? But so that's kind of neat. I don't know if anyone out there has ever hyperventilated. I have. I get panic attacks occasionally. They started in grad school when I'm really stressed about something. And I start hyperventilating. I start breathing uncontrollably fast, and you start feeling dizzy. It's, how do they put it here? Increased rate and depth of breathing, numbness, lightheadedness. That's how it feels when you're hyperventilating. And you really have to, it's usually anxiety provoked. And as it says, the treatment is to eliminate the anxiety provoking thing. So to calm yourself down will help to slow your breathing rate. But also breathing into the bag can help to reduce some of that dizziness and stuff that's caused by the alkalosis of the blood. So some little practical tips here, the chemistry behind hyperventilation. So that is Chapter 8. I don't know how long I talked for. I didn't time myself, but it feels like more than 2 hours. So if you need to rewatch parts of this lecture again, feel free to. If maybe you stopped it and watched it in 2 parts. And let me know which parts are particularly confusing for you so that maybe I can arrange some kind of a review lecture where I go do a second lecture on Chapter 8 that's maybe 40 minutes long that touches on some of the more confusing concepts. So hopefully you are feeling like acid and base chemistry is something that you're grasping, and doing the homework problems, read the chapter, work through the homework problems, and contact me if there's any issues. Go to the LAC if you're having problems with your calculator, and always, I encourage you to study with classmates. If that's a possibility, and work together and help each other. So that's all. Goodbye.